Okay, welcome everybody to the latest seminar of the International Network on Quantum Annealing. It gives me great pleasure to introduce today's speaker, who is Ernesto Acosta, who has a joint appointment between the Complutense University in Madrid and the University of Granada. And Ernesto will talk to us about adiabatic training for variational quantum algorithms. Over to you, Ernesto.
Thank you, Paul. Thanks for the invitation. Very glad to be here, participating of the seminar. So this is part of my PhD research, where we are using quantum annealers, running adiabatic algorithm to solve a specific problem in computer science, which is the optimization of variational quantum algorithms. So before going into the very specific details of the adiabatic training, I would like to go through first the motivation of this problem, and just contextualize some of the main ingredients on the machine learning problem we're dealing with, and then just we will be able to go into the details on how we model the solution using adiabatic quantum computation for a very specific real case problem, which is time series prediction on the stock market time series. So the main idea is that quantum machine learning and artificial intelligence is nowadays everywhere, from ChatGPT to social networks, etc. So it's a normal ingredient in our everyday life. And so quantum computing has emerged with very high attention in the last few years, although it was defined like 4 decades ago. It started to get good track in the last few years. And in the quantum computing, as you may already know, there are two different approaches. One is the gate-based approach, where companies like IBM, Microsoft, etc. are making implementations. And then we have the quantum annealers, where we have D-Wave, very different approaches, both using quantum mechanics to undergo the computation. And it is one of the main research areas in quantum computing is quantum machine learning, which tries to model or help on the regular machine learning area, regular artificial intelligence area, either adopting the models from the classical machine learning or helping to accelerate or improve those models. And in this quantum machine learning discipline, one of the most active approaches is these so-called variational quantum algorithms, also known as parameterized quantum circuits. Some others call it quantum neural networks. So it's a very recent research area, which is in very active development. So it still doesn't have a very strong, solid foundation. So there is a lot of research there. And it requires a very heavy training process, meaning this particular VQA model needs to learn from experience. And this learning nowadays is run on classical optimizers, running on classical computers. So we asked ourselves if quantum annealers are known to be great optimizers and training parameterized model is an optimization process. Is there a way to combine both and have a quantum annealer being the optimizer for a parameterized quantum circuit? And if there is a way, does it show any practical advantage? So this is what we are going to dissect in the following slides. So before we go into the details, just a very brief recap or context on the parameterized quantum circuits. Those are inspired by traditional neural networks, which are composed by so-called neurons, which are computing units that receives inputs from another neurons, which are multiplied by some weights, and they are combined or summed up so that this aggregated value triggers the activation function of the neuron. So it will then output either 1 or 0 or another value in between, depending on this activation function. Then one can stack all these neurons by layers, and by so building a whole computing model. The main goal for this neural network model is to have it be able to predict with higher accuracy the output based on some specific inputs, and this model will be composed by neurons, and the connecting edges between neurons are so-called weights. So the goal is to find the proper weights to connect each of the neurons together, so that for every input that we give to the neural network, the predicted output is correct. And for this process, you give the neural network a set of known values, which is the history on top of which the neural network will build its learning. And those inputs and outputs are collected in a so-called data set, which as the larger it is, the better the learning of the neural network will be. And it requires an iterative process. So the idea is that you give the neural network each one of the records on this data set as an input, then let it run the neural network and give you a predicted value. In this case, for instance, is 0.85. The goal of the trainer is to compare this output, this 0.85, against the expected value in the data set. Let's say it was supposed to be 0.9. So the difference, the 0.05, will have to be readjusted backwards through the whole neural network by adjusting these connections, these weights between neurons. Okay, and this is all the classical way to build and to train neural networks. But it will be pretty much the same on these variational quantum algorithms. Here we see one particular case of neural network, which is the recurrent neural networks, which is one of the models used to train time series, to predict values on time series, which is the one we will implement in the quantum algorithm. And now, moving into the quantum computing world, this is the general model of variational quantum algorithms, or variational quantum circuits, or parameterized quantum circuits, which act similar to a regular neural network, as we just saw. Not in the same way, but this is a model which has a lot of parameters that need to be adjusted through an optimizing process, so that the whole circuit, the whole algorithm, is able to predict unknown values based on the learning achieved from historical data that it was previously used for training. So these variational quantum algorithms are designed and run on the first model of quantum computing that we mentioned before. So in these gate-based quantum computers, and it's composed by 3 parts: one data encoding subcircuit that takes classical data and translates it into a quantum data by using rotational gates. Then you have the precise variational circuit, which is composed again by quantum gates, single qubit gates, or control gates that map all these network and establish all the entanglement between qubits, and then a partial measurement part at the end to extract the output of the circuit. Then this output is read by this optimizer, compared against the expected value, and then the rotation angles are updated back to the variational circuit to run again the cycle until the model is able to predict with high accuracy the expected values. So as I mentioned, this is one very active area, because with small circuits, one can get pretty good results compared to traditional quantum algorithms. And it is important because at this stage of hardware implementation and quantum computing, the noise, the coherence, and prone to error is very known in this stage of the implementation. And so these quantum computers, as they are known today, are called NISQ devices, because it stands for noise-induced software devices. So in order to take the much advantage of these and today's quantum computers, one needs to design quantum circuits that are pretty small and pretty short in terms of the number of qubits and the length of the number of gates used, so that the coherence doesn't affect the computation overall. However, as a training model, it suffers from what is called barren plateaus, which is the problem that arises when the cost function tends to be flat, and the gradient that is calculated backwards to update these connecting weights, or in this case, the rotation angles, is hard to predict. So for this, there are different training algorithms. One of those is the simultaneous perturbation stochastic optimization. This is a very classical algorithm used to train classical neural networks, nothing to do with quantum, but still is the same process that is being used today to train variational quantum circuits. And for this, the cost function that is used for this optimization is the mean square error, which tries to minimize the difference between the expected value and the calculated value over all the items in the data set. So in this case, let's say we are training a quantum neural network to be able to predict on a different sets of images if the image that is provided is either a cat or a dog. Each of those belong to separate classes that are labeled, let's say, 1 and 0, and we are giving the quantum neural network a data set of 1,000 images of cats and dogs. So the idea of this mean square error, which is the cost function, is to take the sum over all the 1,000 records against for the difference between 1 if it was a cat provided to the model, and the predicted value, which might be 0.8. The difference gets squared, so that to avoid mutual cancellation between positive and negative differences, so each difference is squared, all of the 1,000 differences summed up, and average is calculated. And the idea is to update all these parameters until this overall mean square error is reduced to the minimum. So by doing so, in several iterations, one might start with a very high MSE value, and slowly, you will get to a very accurate value, which is called the convergence point. And variant plateaus will show cost function very flat, as I mentioned. And the idea is to avoid these situations or be able to overcome it with different alternatives for training. One of those is the one we are presenting here. So as we saw earlier, there is a type of neural network, traditional neural network, which is called recurrent neural network, in which one node can be input its value to itself, and it can be unwrapped or seen unwrapped as the image on top. And this one can get translated into quantum terms as a quantum recurrent neural network or quantum recurrent variational quantum algorithm. In this fashion, where we have a number of recurrences of the same pattern. In this case, we are seeing 3 recurrences of the same algorithm, and this was a model 1 year ago by a team of researchers in the University of China, and this model is the one we implemented, and we changed the classical optimizer with quantum annealer. So let's dissect it by pieces. Each block that is being stacked along the recurrency timeline is composed by these 3 parts. So, like a regular variational quantum algorithm, it has data encoding subcircuit, which in quantum machine learning offers different alternatives: basis encoding, amplitude encoding, angle encoding, frequency encoding. For this particular model, we used amplitude encoding, which takes input value, input classical data, performs a quantum operation as a quantum gate, and translates it into the amplitude for the input state vector. We will see it in few slides how it's done. Then we have a ansatz subcircuit. Again, for this one, there are different alternatives in the quantum machine learning literature: nearest neighbor, secret block, all-to-all, which defines different types of interconnection between qubits to define entanglement. So nearest neighbor implies connecting each pair of consecutive qubits, qubit 0 with qubit 1, qubit 1 with 2, 2 and 3, and 3 with 1. So having a circular encoding scheme. Others imply all-to-all, meaning each qubit is connected or entangled with each of the others, etc. This one is like in the intermediate size of complexity and efficiency, because the more entanglement you establish, the longer the circuit, and the longer the circuit, the more prone to noise and decoherence. So this approach, this nearest neighbor, is the one in the middle. So the problem we are trying to solve by this model is a time series forecasting, for which there are different alternatives, and we are focused on the recurrent neural networks approach, but on the quantum fashion. So it'll be a quantum recurrent neural network to predict future values on a time series. And we selected specifically the time series for stock values for listed companies in the New York Stock Exchange. We use time series for Banco Santander, for AT&T, and others, which are very long time series. So that offers a very long and big data sets. And the proposed architecture for this is a classical computer that is like the orchestrator of all the data flows between every component. Of course, starting with gathering all the data set from the external data source, which in this case is Yahoo Finance, and then build or design the quantum circuit, which runs in a quantum and a gate-based approach quantum computer, which is the IBM quantum computer, handled by the Qiskit library. On the other side, this classical computer is the one that is feeding the quantum annealer computer. In particular, this is the D-Wave computer, where we are running the adiabatic process to train this quantum circuit. So the classical computer retrieves the data from the external source, defines the quantum circuit. From this quantum circuit, we extract the input state vector and output state vector for each of the records on the data set, and the ansatz operator. These three elements are the ingredients for the adiabatic computer to run the Kubo formula, find the minimum energy on this setup. With this minimum energy, identify the optimal rotation angle values for this quantum circuit, and then have it complete for validation. And all these data flow replaces the traditional classical training that takes place usually in a classical computer. So our goal is to replace this box, this classical training box, with all these elements in an adiabatic computer. This is how the quantum circuit is seen once implemented. So the original quantum recurrent neural network that we saw on with the yellow boxes, it's translated into this circuit, where we see the three recurrences. The quantum recurrent block is repeated 3 times, so that we can input 3 historical values for the stock prices on the listed company to predict the 4th value. Okay, so dissected or detailed the quantum circuit is seen like below. So in total, it has a dimension of 4 qubits and a total of 48 gates, making 3 partial measurements along the execution. This is important because complexity in quantum computing is measured by the size of the circuits, number of qubits, number of gates. And our implementation allows to define more recurrences of the quantum recurrent block. So it could be 3, 4, 10, 12, etc. And longer circuits in terms of qubits. But again, if we take it very long, noise and decoherence will start to take more presence in the circuit and affecting the calculations. So in order to perform the training, we have this quantum recurrent block. We need 3 ingredients. First of all, we need a way to translate this input data to the quantum annealer. First one is this, to translate the input data as an input state vector, which will take place in this optimization function, which is the MSE. And the calculated value, we need to compute the quantum operator over the input value. So first we need to translate real data from the data set as an input state vector. So as an example, we have the entry for the 8th of July of 2024. It was the value of the stock of this company was 66 euros 53 cents. First thing, we normalized this value so that all the values are between 0 and 1. So this specific value will be 0.58. This data encoding strategy implies calculating ARCO cosine for this value, which becomes 0.95. This is computed in 2 input qubits in the register D for data. Then we have another 2 qubits for register H for hidden. So in total, our circuit is composed by 4 qubits, 2 input data qubits, 2 hidden qubits. In those 2 input qubits, we encode the same value just to amplify the input vector. And then with this value, ARCO cosine of 0.58, we get 0.95, and translated it into a state vector, we will have this representation. Since we are encoding it in the 2 uppermost qubits, we will have positive values only for statuses 000, 010, 100, 1100, which are the components 0, 4, 8, and 12 in a state vector. Since we have 4 qubits in the registry, our quantum system will have 2 to the 4 total values. So the input state vector will have 16 elements, and we'll have values only on the component number 0, 4, 8, and 12. And by this configuration, this particular value 0.95 will have this representation: 0.79 for status 000, 0.41 for status 0100, etc. Also, we need to define the output state vector, which is the first component on the MSE function. So, for instance, for the same entry in the dataset, the 8th of July 2024, the price increased compared to the closing price from the day before. So we are labeled increase with 1, decrease with 0. In this particular case, the price, the stock value of this day increased compared to the 7th of July 2024. So defining it as a state vector will be equivalent to having a readout of a value 1 on the uppermost qubit. So out of the 4 qubits, we are reading the first one. So we will have positive values only for, in the whole state vector. We will have positive values on component 000 and component 1000, which are 0 and 12, positions 0 and 12 in the state vector. So in this case, price increase will be represented by this state vector. So we have the second ingredient for our quantum adiabatic algorithm to run. The third one, which is the most complex, is to translate this ansatz subcircuit into a matrix representation so that we can involve it in the optimization function, which is the one taking place on computing the calculated value for any specific entry in the dataset. So this Q operator represents the action of this ansatz subcircuit in the whole process. So in this particular case, we are incorporating rotational qubits, rotational gates on the second qubit, controlled by the first qubit, and this is a rotation on the z axis. a rotation angle. So this subcircuit has this matrix representation, this quantum operator matrix, which is a 16 by 16 matrix involving exponential values on each of the 4 rotation angles. So we are parameterizing these 1, 2, 3, 4 rotation angles. And this particular subcircuit has a quantum operator represented by a diagonal matrix. So we have non-zero components only on the diagonal. To simplify it, we will see it in this way. So this will be the element 0, 0 on the matrix. This will be the 1, 1, etc., up to the entry 16, 16 on the matrix. So by doing this, we have all the 3 elements that we need to compute MSE. We have expected value, calculated as the output state vector. We have the quantum operator, which is this matrix, and we have the input state vector, which is required to calculate the output value. Now we have all the MSE formula that we will use as an optimization formula. So now entering to the quantum annealing part. For quantum annealing to be used, we need to define a QO formulation for the adiabatic process, which requires 2 main elements: a function to minimize, composed by binary variables and real coefficients. These binary variables are these x, the coefficients are the z's, and this function is subject, or can be subject, to certain restrictions that we can define based on these variables. And the quantum annealing process will start with a very simple Hamiltonian of the system, and will evolve onto the target Hamiltonian defined by this minimization function, being able to find the lowest energy value, which will be the solution for this minimization function, which involves the parameterized rotation angles. And this is a potentially good alternative to classical trainer, because thanks to tunnel effect and this adiabatic evolution, the training process can jump or can get out of local minima, like these first values, to a global minima, which will be the efficient solution for the problem. With classical training, the training process goes by computing the gradient of this curve, and if you hit a local minima, you hit a value on these valleys here, it is very hard to move into the next one, or to move to the best one, the global minima, by computing gradients. So this quantum annealing process offers a potentially good solution to get out of local minima and be able to explore other better global minimas, or even to go to the optimal solution. So by doing this, we replace the classical trainer with an adiabatic optimizer. Our function to minimize will be just the mean square error that we just built before. And in this case, since we are reading only 1 qubit out of the 4 qubits in the circuit, we can just rely on the difference, the mean square error difference in these particular elements on the state vector, the element 0 and the element 8, which are the ones reflecting measurements on the topmost qubit. And the conditions, the restrictions will be just to have one unique value per rotation angle. So we cannot have two different values as a best solution for one rotation angle. So it is very, very simple to define the constraints here. Just to see it more clearly, this is a very, very simple circuit. This is not the one used to predict the time series, but just to understand the whole process, how it's defined. So we have a circuit with two qubits, two gates, one single qubit rate and one 2-qubit gate. In this case, our quantum system will have four possible values. So we have a state vector composed by 4 elements, 0, 0, 0, 1, 1, 0, 1, 1, each of these with potential values, amplitude, probability amplitudes, alpha, beta, gamma, and delta. We have our quantum operator acting on this input state vector, which is the effect of each of these quantum gates, rotation on x-axis for the qubit 0, or controlled rotation on the second qubit, generating the state vector 1. Each of these gates will have a matrix representation acting on the input vector, computing all these dot products will bring us all these expression. So it will be a vector with 4 elements. Each of these records, which will comprise the amplitude probability times the effect of these sine and cosines, which correspond to the rotation gates. Then the first thing is to expand this expression so that it can contemplate the possible values for each angle. So since we are having discrete values for it, we need to discretize the angles or the trigonometric expressions or the exponential expressions. In this case, we are having sines or cosines. So we want to split the range. In this case, we are moving from 0 to 2 pi. And we are discretizing it in segments. In this example, we are discretizing in 8 segments from 0 to 7. We are pre-calculating the sine and cosine for each of the values so that we can incorporate it into our QUBO formulation. So this is the preparation for the QUBO formula. We have this ansatz operator acting on the input state vector. So we have cosine for the theta 0 minus sine theta 0, etc. If we are going to expand it, each of these terms involving one of the angles will be amplified to 7 values. I mean, to 8 values, because we are splitting it from 0 to 7. So we will have to expand and replace each of the occurrences of, in this case, cosine theta 0. It will be expanded to cosine theta 0 first value, which is 0, cosine theta 0 second value, which is pi divided by 8, etc. And by so this single term will become a sum of 8 terms, where the cosine theta 0 divided by 2 will be these values, 1, 0.98, 0.923, etc. And we will involve this variables, which are the binary variables, which will act as coefficients. And we do the same for each of the summation terms. So one specific example, we have this input value or input state vector, square root of 2 divided by 4 for the first value of the input state vector, square root of 2 divided by 2, etc. We apply the quantum operator here, cosine of the first angle divided by 2 applied to the first probability amplitude, minus I sine first angle divided by 2, multiplied to the second value of the second attribute of the input state vector, etc. Amplified, it will become like this. So this cosine theta 0 divided by 2 will be expanded to 8 terms, cosine 0, cosine pi divided by 8, etc., etc. And we will have a very long expression, in this case composed by 4 summation terms, expanded 8 times, it will be 32 terms, and we'll have to do it the number of times as our data set contains records for training. So the actual case we are dealing with for this quantum recurrent neural network on time series prediction will have this shape. Our ansatz operator, as we saw, is a 16 by 16 matrix. Each of the elements will have this appearance, exponential, plus minus, one angle divided by 2. And we will discretize our function, in this case, the exponential function, in 7 segments. We are taking the values from 0 to pi. We are not considering minus pi to 0 because all the operator expression already incorporates positive and negative values. So we can focus on discretizing from 0 to pi. And the restrictions will be just to have one of these potential values as a potential result on the formula. The details of the experiments we run for, as I mentioned, different companies. One of those was Santander Bank. So we took real data for this company. We took 250 records, which are more or less 1 year of stock prices. We encoded it in 2 data qubits, which make in total 4 qubits for the circuit. We involve 3 repetitions of the quantum recurrent block. We use 100 epochs for the classical trainer. We experimented with 1024 shots for the circuit each time it was executed. We discretized the function in 4 parts, and we run it on a general PC. This is just one simple example of the output of the execution, where we have, in this case, 16 potential values, meaning we have 4 angles, W, X, Y, and Z. Since each of these angles may have one of 4 potential values, because we are discretizing in 4 potential values of the rotation angle, we can have 16 binary variables, where only one can be positive out of these 4 W's. One for the X, one for the Y's, one for the Z's. And this, once de-discretized, will become like this. So if it is the third potential value for the W, meaning theta 0 will have value 0.3125. For X, we got as the optimal value the second potential angle, meaning 0.178, etc. So the results are very interesting. Initially we were pushing or waiting for better accuracy, but what we saw in the end was in average the same accuracy as using classical training, but much better training time. For comparison, we use also a traditional neural network, so we are comparing variational quantum algorithm or quantum recurrent neural network classically trained, the same circuit adiabatically trained, and just a traditional neural network, just to see how well it behaves. We run it for different companies. Here we are showing value for Santander and AT&T for 150 records using 2 or 3 repetitions of the quantum recurrent block, discretizing in different segments, 4, 5, 6, or 7, and the accuracy was pretty much similar between the three different models, but as I just mentioned, execution time was very much slower, lower in the adiabatic training compared to classical training. That is because on classical training, you are depending on epochs, cycles, training cycles. As we saw before, we use 100 training cycles, which is the average. For each cycle, the circuit needs to be executed the number of times of the data set. So in this case, 150. And since the quantum circuit needs to be executed for a number of shots to take the average, in this case, 1024, that means you need to go through the quantum circuit 100 times, times 150 records, times 1000 shots. That takes all these 4,000 seconds to train, or 2,000, well, 13,000, while in the quantum annealer, it takes only one adiabatic process because all the QUBO formula contains the data from all the training data set. That's why training effort is much lower than classical trainer. We also run mostly on simulated environments using this Qiskit library, the Wave Ocean, etc. But we run also executions on real hardware, having all these values. In average, better accuracy on the real hardware, and even shorter execution times. We experimented with different configurations of the circuit, playing with different number of repetitions of the quantum block, bigger number of qubits, discretizing in smaller segments, etc. The best combination we saw was increasing the number of quantum repetitions. So when going from 2 to 3, 4, 6, etc., the accuracy was getting better. That is explained because the longer history you consider for training, the better you will be able to predict the next value. And in the same sense, the deviation for each execution compared to the mean gets smaller as the number of repetitions is increased. So in summary, we were able to define a hybrid methodology, but purely quantum methodology involving gate-based model and adiabatic model, quantum to quantum. So there is no classical training here. It was implemented and tested on a real case scenario. Although there is no quantum advantage, there is also no disadvantage, which is good news. So the model doesn't perform worse than the previously known classical trainer, but we saw higher efficiency in terms of execution time, which might imply lower energy consumption in the future. We saw also that by discretizing the search space, the angle rotation possibilities, reduces the expressibility of the model, because we are losing the values in between. And this enters into the area of no gradient dependent trainer, which might help also to overcome these barren plateau or vanishing gradient effects. And this can be a good candidate to enter into the high performance computing schema as a potential accelerator. So this is the data of the paper where we documented all this process, and the document where the quantum recurrent neural network was defined. A couple of recommended lectures on quantum machine learning that we use to model our proposal. And thank you very much. I'm open to any questions you may have, or any comments, suggestion, critics.
Great, thank you very much, Ernesto. A round of applause from me on behalf of everyone in the audience. And as Ernesto says, if there are any questions, please raise your hand or just speak up or whatever.
In any case, you can reach me out later on. You just send me an email.
There's a question from Craig.
Yes, so how general is this method? So would it work for, say, a variational quantum eigensolver? I wasn't, so there we have a kind of classical optimizer training a circuit, but it's not clear to me how to convert that into a Cubo problem.
Yep. Yeah, I got it. Thank you for this question, Craig. Yeah, it's general up to the point where you need to define this operator matrix. It has to be done. It's not automatic. The translation of these ansatz into the operator matrix that is involved into the MSE. So depending on the architecture you define for this ansatz part, you will have a different matrix that will have to be handled, let's say, by hand. Actually, we played with different combinations of ansatz, and by so we got totally different operator matrices. This one, by coincidence, is a diagonal matrix, which is very easy to, or much easier to operate than more sparse matrix. So it is general up to this point where you have to deal specifically with the ansatz you are incorporated in your circuit.
Okay, that's great. Thank you.
Welcome.
And any other questions? Maybe I could ask a quick question. Could you go back to page 27, please? Yeah, perfect. So your real hardware, does that mean both the quantum annealing hardware from D-Wave, presumably, and the gate-based hardware from IBM?
Yeah, correct.
And I'm perhaps a little surprised there isn't more latency in the communication channel, which goes via your classical control computer in the middle.
Yeah.
How do you manage to keep the latency down?
Yeah, here we are. I mean, this time is just the execution time.
Okay.
We didn't consider all the communication because it can take, I mean, minutes or even hours.
Yes,
You are very far in the queue.
yes, as I understand, and that's always going to be a problem with any variational approach.
Yeah, absolutely.
See, and I guess you have double the problem because you're doing both.
Exactly. Exactly. You have to queue for the IBM and then queue for the D-Wave, and
Interesting.
yeah, that's true. But this is just the execution time of the training in the D-Wave computer. All the communication and all the execution in the IBM Quantum was not considered here, just to take measures of the actual training.
Okay, understood. Fine. Good. Are there any other questions for Ernesto? If not, let's thank Ernesto one more time. Thank you very much, Ernesto. Lots of interesting things. Good to see some real data on real machines, as always. And let's conclude there. Thank you very much.
Yep. Thanks to you, Paul, and all the audience. I'll be following the next seminars.
Cool. Excellent.